Well, thank you everybody for joining this week's Wednesday seminar. It's my great pleasure to introduce a good friend and a colleague of mine, Dr. Xiaomeng Jin. Dr. Jin is an assistant professor at Rutgers University. She is an expert in atmospheric chemistry and using remote sensing and data modeling to study a variety of issues related to air pollution, wildfire, and its sources, impacts, and connections to human sectors. Dr. Jin has done a lot of amazing work. Among a lot of her honors, she is a recipient of the NASA New Investigator Award last year, this year? Last year. Please, so one thing I have been knowing Xiaomeng for many years, and we have some collaboration. So one thing I really admire about her work is she has both the technical depth that's leveraging the latest remote sensing and modeling works, as well as really apply them to societally relevant, interesting work. So without further ado, please join me to welcome Dr. Jin.
Thanks, Minghao, for the nice introduction, and hello everyone. Thank you for being here. And so the work that we have been working on at Rutgers University is trying to bridge remote sensing observations with near-surface air quality. And so the work that I'm going to present today is to talk about how we can use the remote sensing observations from space to understand this Ozone-NOx-VOC chemistry for both urban and fire plumes. Okay, so over the US, there have been a lot of efforts made to improve the air quality. So under the Clean Air Act, we see that there's a lot of reductions of these emissions of common air pollutants. So the common air pollutants emissions have reduced by about 74%. So this progress occurred while at the same time the US economy continues to grow, people drive more, and population and energy use both increased. So which is great news. But even with these large reductions of emissions, air pollution is still a problem in the US. So here I'm just showing you is the number of the people living in counties where the air quality is above the standard in 2023. And we can see that in the US, there are about 140 million US people in the areas where this air quality is above the standard. And there are about 130 million US people living in areas where the ozone air quality alone is above the standard. And actually, as you can see on the figure on the right, which is showing you the areas, the ozone non-attainment areas in New York and New Jersey region. And we can see that in many regions in New York, New Jersey, including Long Island, and also almost every county in New Jersey are in this, what we call the ozone non-attainment areas, where the ozone is above the standard. So one of the reasons why ozone is very difficult to control is because of these non-linearities of ozone chemistry. So generally, the ozone is a secondary air pollutant, and it is mainly formed through these photochemical reactions between two precursors of ozone. And one is called oxides of nitrogen, or NOx, so which are mainly coming from the fossil combustions and vehicles, and the other is called VOCs, or volatile organic compounds, so which are these other organic compounds in the atmosphere. And while the anthropogenic emissions can also emit VOCs, but globally, the majority of these VOCs are coming from these biogenic activities from trees. So the ozone production is dependent on the relative abundance of NOx versus VOCs. And so this figure I'm just showing you is showing you an ozone isoplus that describes how the ozone production is non-linearly dependent on its precursors, NOx and VOCs. So essentially, when the NOx is relatively low over this area, we can see that the ozone production increase with increasing NOx. Over these areas, we call this ozone production as NOx limited. As we further increase NOx, over here, you can see that at relatively high NOx, we can see that this ozone production increase with increasing VOCs, but it can actually decrease with increasing NOx. So why is it important? It's because depending on whether the ozone production is NOx limited or VOC limited, and the ozone and the effectiveness of emission control can also be very different. So say if the ozone production is NOx limited, then it is more effective to control NOx emissions. But if on the other hand, if we see that the ozone formation is in this area, which we call this VOC limit or NOx saturated regimes, and the VOC emission reduction is more effective, and the NOx emission reduction is actually counter-effective, which means that reducing NOx emission could actually make the ozone pollution even worse. So that is what we call these nonlinearities of ozone chemistry. So traditionally, we generally rely on using in-situ measurements to understand this ozone-NOx VOC chemistry. And the US EPA has established this air quality system network, so where they just place ground-based monitors across the country. So while we have a relatively dense AQS network, but still it is impossible to place monitors everywhere. So for example, in New Jersey, as you can see on the right, there are only about 18 ozone sites in total in New Jersey. So which has very limited capability to capture the spatial distributions of ozone precursors and also these relationships. Considering these limitations of in-situ measurements, so the way that we are proposing to do is to use remote sensing observations to understand these ozone-NOx VOC chemistry. So the such a remote sensing of atmospheric composition generally relies on observing these either the backscattered solar radiation or the thermal infrared emissions from the Earth. And essentially, so the remote sensing of these trace gases relies on observing these spectral signatures of gas absorptions. So some gases, such as formaldehyde SO2, they have spectral signatures at UV wavelengths. Some, like nitrogen dioxide, they absorb visible light. And others, like CO2, methane, which are greenhouse gases, they have stronger spectral signatures in the near-infrared thermal bands. And so the retrieval of these trace gases is essentially an inverse radiative transfer problems, which we can solve these spectral signatures that is measured from space by matching them using a inverse radiative transfer model. And so the instrument I'm showing you here, and this instrument I'm showing you here are just some of the instruments that we use for retrieving of these trace gases from space. And this showing you on the left are those instruments that covers the UV to visible wavelengths, and this showing you on the right are the satellite instruments that covers mostly the thermal band. Okay, so the satellites, they move around the Earth at a given orbit. So we call this. So there are two major types of orbits that have been used in our research. So a lot of these Earth observing satellites like Aura, Alpha, Sentinel-5P, which I'm showing you here, are in this what we call this lower polar orbit or the sun-synchronous orbit. So for the sun-synchronous orbits, so the satellite orbits over the poles from the north to south directions, and they move a little bit westward in each trip. And you can think about this as like the peeling an orange, like piece by piece, and one strip at a time, you will be able to cover this globally. And one important feature of this sun-synchronous satellite is that it always overpass a certain area of the Earth at the same local time every day. And depending on the viewing angle, also these swathways, the global coverage can be achieved in about 1 to 6 days. So this is sun-synchronous satellite. So on the other hand, the geostationary satellite, they orbit around the Earth over the equator, and they are rotating at the same speed as the Earth's rotation. So they are stationary to the Earth. So because they are stationary, so they can take as many pictures as you want. And generally, the geostationary satellite instrument can give you high frequency observations, like hourly observations, which would then allow you to observe, for example, diurnal cycles of the Earth's process. But the issue with the geostationary satellite is that it only covers part of the world. So in order for the geostationary satellite to rotate at the same speed as the Earth, they have to be very high altitude, which is around 36,000 kilometers away. So this actually makes it very challenging for this geostationary satellite instrument to see these tiny details of the Earth. So this is also why that it was only until very recent years that we were able to have geostationary satellite instrument of atmospheric composition. Like for example, the GEMS, which covers East Asia, was launched in 2020. And Temple, which covers North America, was launched in 2023. And the Sentinel-4, which was just launched this year in July, covers the Europe. Okay, so in our group's research, we use both observations from the sun-synchronous and the geostationary satellite instruments. And hopefully by showing results from both types of instruments, you can get a sense about what are the pros and the cons of different satellite orbits. Okay, so this is showing you is this of the satellite retrievals of nitrogen dioxide from OB, which is called ozone monitoring instrument, that is on board this Aura sun-synchronous satellite. And with this, so this Aura satellite was launched in 2004. And now we have about more than 20 years of observations from Mars. So with these OMI global observations, we can see from globally where there are hotspots of air pollution. And we can also see that how this NO2 pollution has changed over time. So this, if you look to compare the level of NO2 in 2005 in 2018, and you can see that the NO2 level has mostly decreased in like US and Europe, but it's actually increasing in regions like in India and China. And so this is supposed to be an animation of a temple, but unfortunately, because of these issues with this with my slides, so we cannot show this animation. But you can imagine that this is like the view that can be covered by temple. So the temple was launched in 2023, and with the temple observations, it now gives us a view of these hourly variations of NO2. So with this our observations, we can then look into these short-term variations of NO2, which unfortunately you cannot see here, but you may also check out this from this website. But one thing I want to note here is that the resolution of temple is actually better than those from the sun-synchronous satellites, which is really like a great breakthroughs that can allow us now to see these NO2 pollution at very high frequency. Okay. So just coming back to this topic about ozone, and want to first clarify a little bit which ozone I'm talking about, because ozone can play very different roles depending on where they are located. So the ozone, in atmosphere, more than 90% of the ozone are in the stratosphere, which forms the ozone layer. And we call this is part of this good ozone because they are like the UV shield that protects us from the harmful UV radiation. So in the upper troposphere, the ozone is also important greenhouse gas. And in this middle troposphere, ozone is a source of hydroxy radicals, which is a cleanser of many air pollutants. But the ozone that we care most about for air quality is actually the near surface ozone, which we call like the nose level of ozone. That is part of the ozone that we can breathe in. And this part of the ozone is what we call this local ozone air pollution. And this is what we call this bad ozone. And if you think about to relate this to remote sensing, so while we know that the satellite instrument can retrieve the total column ozone, but if you look into the vertical distribution of ozone in the atmosphere, we can see that the majority of the ozone is in this stratosphere. So the contribution of the near surface ozone is just too small to be detectable from space. So this then brings the question about how can we actually use remote sensing observations to see the ozone pollution if we cannot even see them from space. So to answer this question, and we just mentioned that the ozone is mainly formed through these photochemical reactions between its precursors, VOCs, and NOx. And while we cannot use satellite instrument to look at ozone pollution directly, but we can use satellite instruments to look into these ozone precursors, VOCs, and NOx. So the way that we bridge ozone chemistry with remote sensing is that we use satellite retrievals of two species that are indicative of ozone precursors. So for VOCs, we use satellite retrievals of formaldehyde because formaldehyde is an intermediate oxidation product of many VOCs. And for NOx, we use satellite retrievals of an NO2 tropospheric column, so which is because that NOx mainly exists in the form of nitrogen dioxide in the boundary layer. And with these satellite retrievals, what we do is that we can take the ratio of these two, which can give us information about the relative abundance of NOx to VOCs. And generally speaking, and high formaldehyde NO2 ratio would indicate that the ozone formation is more NOx limited. And the low ratio, on the other hand, often means that ozone production is more VOC limited or NOx saturated. So if I just mentioned that if it's NOx limited, it's more effective to control NOx. And if it's more VOC limited, it is more effective to control VOC emissions. So this indicator has been proposed for a long time. And it is also very easy to use and essentially just take the ratio of them. But the question is, how high is the high and how low is the low? That is, what is the threshold values to separate these two regimes? And whether these threshold values varies in different environments. So that is a question that we are trying to solve. to understand how well that the satellite data is able to capture this on chemistry, we first did is using what we call a top-down approach, in which we just directly make the connections between this ozone from ground-based measurements versus those from satellite data. So what I'm just showing you here is showing you this is that we collected millions of ground-based measurements from the EPA AQS network, and then we aggregate these observations according to their corresponding alternative formaldehyde level, which are sampled from satellite data. And then we look into, so the color here is represent this ozone exceedance probability. And you can see that these figures kind of mimic these patterns of these ozone isoplanes. That over these areas, we can see that the ozone exceedance probability increase with increase in NO2, which means that ozone exceedance is more likely to occur with increase in NOx. So this is what we call this NOx-linked regimes. And over this area, we can see that the ozone exceedance probability actually decrease with increase in NO2. So this is typical of this NOx-saturated chemistry. And we can see that the transition occurs somewhere between 2 and 4. And this is also where we find this highest ozone exceedance probability. Okay, so this figure on the right is showing you how this ozone exceedance probability is correlated with this OMI formaldehyde ratio. And you can see that there is indeed some of these correlations between these, and the satellite data is able to indicate some of the nonlinear chemistries by showing this nonlinear relationship. But you can see that these regime threshold values for different cities, like which is represented as this peak of this curve, can also vary for different cities, for different locations. So one of the advantage of satellite data is that from satellite data, we can not only have this full coverage, but we can also have this long-term continuous record of satellite observations. So this is, for example, showing you for Chicago how this NO2 for the satellite observed NO2 and formaldehyde has changed over time. And this is showing you that which is showing you the blue is showing you for NO2 and the green is showing you for formaldehyde. I'm showing you here for 2 different periods, and as a function of the distance from city center. So what you can see here is that in the early period, there is a sharp urban-rural gradient of nitrogen dioxide. But because there has been a lot of emission reductions that happened in the past 2 decades, we do see that there is actually a large reduction of this NO2 gradient in Chicago. And for formaldehyde, so formaldehyde is mainly coming from these biogenic activities on trees. So which we don't see much of these urban-rural variations, and we don't see much of this trend during this time period. So if we take the ratio of these two, which is showing you like this red line here, and we can see that the ratio of this formaldehyde to nitrogen dioxide has increased in the recent period, which means that the ozone production in these regions has become more NOx limited. And if we look into these intersections between this gray band and this red line, which indicates where is regime transition occurs, we can see that the regime transition has actually moved towards the city center from around 120 kilometers away from city center to around 30 kilometers away from city center. So this is what we see from the satellite. And then if we want to see what happens in the ground, so this is showing you based on ground-based observations of this ozone as a function of distance to the city center, and again in 2 different periods. So we can see that in this urban cores where the ozone formation is not saturated, we can see that the ozone actually increased in response of this NOx reduction. But the further away from the city center where the ozone formation is NOx limited, we can see that there is indeed large reductions of ozone. And in this early period, we can see that the peak of ozone is around 120 kilometers away from city center, which is actually where we see this regime transition. And also in this recent period, this peak ozone has moved towards city center to around 30 kilometers, which is again consistent with the regime transition. So from this, it tells us that some satellite data, it can indeed give us some information about these urban-rural variations of these ozone production regimes and how it has changed over long term. Okay, so just talk about the ways that we can use satellite data to look into the ozone chemistry, but there are still some problems or some uncertainties of using this method. So what are these uncertainties? So the first uncertainty is that we use satellite retrievals, but what the satellite retrievals gives us is just the vertically integrated column densities. But for air quality, what we care most is just the near surface environment. So depending on the vertical profiles of NO2 and formaldehyde, the column surface relationship of these two can also be very different. Another thing is that we are using NO2 as an indicator of NOx, but these partitionings of NOx can also vary in different chemical environment. And third is that we are using formaldehyde as an indicator of these thousands of different VOCs. But as you know that there are all the different kinds of VOCs, and the formaldehyde yield from different VOCs can also be very different. So how we can use this formaldehyde indicator of VOCs is also uncertain. And another thing is that the ozone formation is essentially at photochemistry, and how much ozone is formed is dependent on these recyclings between hydroxyl radicals and the NOx. And this production of hydroxyl radicals is also dependent on the availabilities of sunlight and water vapor, so which can also vary a lot in different conditions. And then beyond that, there are satellite retrievals always have uncertainties, which could further complicate our interpretations of using satellite data to understand its ozone chemistry. So given these uncertainties, the other thing that we are currently working on is trying to figure out what are the uncertainties of this, and which of these factors is more important, and how these factors could influence our interpretations of this ozone chemistry in general. Okay, so this is what we do. So for this, to understand these uncertainties, what we do is that we are using a bottom-up analytical approach, in which that we start from these box models that solve these ozone production dependence on NOx and the VOCs. And so this is showing you, for example, this ozone isoplex that is derived from these analytical models. And what we are very interested here is trying to figure out where this regime transition occurs, which is essentially this red and blue line here. And from this box model, we can derive this regime threshold for VOCR to NOx. But to link this with this set of retrievals, and we need to get from NOx to NO2 column, from VOC to formaldehyde column. So what we do is that we are using a chemical transport model, 3D chemical transport model, GeoChem, to simulate this local relationship between formaldehyde and the VOC, NOx and NO2, and also the column surface relationship of NO2 and the formaldehyde. And from this, we can convert this ozone isoplex now as a function of this NO2 and the formaldehyde column. And these are the two quantities that we can retrieve from space. And then similarly, we can derive the regime threshold values, which is again is red and blue line. But these regime threshold values can also vary depending on a lot of things, which I'm showing you here. And the advantage of this approach is that because we are building things from bottom up, so that we can test, and this is by basically building things like piece by piece, so that we can test out the influence from individual factors. So that is what the method. And here is showing our results. So this figure is showing you this regime threshold value for column formaldehyde ratio over the US at 2 p.m. local time. And we can see that there is actually some variations of this regime threshold values, which tends to be higher in these urban areas, but tends to be lower in these biogenic emission dominated regions like South and Eastern US. So the figure on the right is showing you which of these factors is leading to these spatial variations of the regime threshold. So the main conclusion I found from here is that a lot of these spatial variations of this regime threshold is due to these variations of this column to surface relationship or the vertical profiles of NO2, which can vary a lot from urban to biogenic regions, so that it can lead to these variations of this regime threshold. And other factors can also have influence, but relatively minor influence compared with this NO2 column surface relationship. Okay, so I just showed you is these spatial distributions of these regime thresholds. But the next question is to think about how it can change temporally. And so this is very important for applications for temporal, which is because from temporal observations, it is a geostationary that can give us our observations of NO2 and the formaldehyde. So we're interested in thinking about how these satellite data can be applied to look into these downward variations of ozone chemistry. So to answer this question, we first need to figure out how these regime threshold values can also vary diagonally. So this figure is showing you based on model simulations how these factors that influence the regime threshold values can vary throughout the day. And you can see that all these factors tend to have very unique diurnal patterns, and they all have different diurnal shapes. So this figure on the right is showing you for New York, for example, what are the regime threshold values and the contributions from individual factors. So this The color lines here I'm just showing is representing these regime threshold values that are derived if we were to only vary one of these factors throughout the day, but keep all other factors constant at 1 p.m. local time. So we can see here is that the regime threshold values tends to be higher in the morning, but tends to be lower in the afternoon. And the high regime threshold value is largely due to this low boundary layer height in the morning. That these two like this that can drag these regime threshold values to be higher. But in the afternoon, because of these competing effects of different factors, we see that they tend to be relatively stable at around 2. Okay, so what I just show you is based on model simulations, which are basically with models to derive these regime threshold values. But if you are familiar with models, you will know that models always have uncertainties. Models can also have biases. And so C1, who is a graduate student in my group, and so what she's been working on is trying to evaluate these model-based regime threshold values using in-situ measurements. So we have 2 types of in-situ measurements. One is called Pandora instrument, so which is essentially a ground-based remote sensing instrument that can retrieve from ground the column of NO2 and formaldehyde. And the other one we have is from the EPA's photochemical assessment monitoring stations or PAM site. So from PAM site, it does provide measurements of NOx and different VOCs. So what she does is that she's basically pairing these measurements together, and so that we can have these ground-based observed regime threshold values. And this is showing you the normalized mean bias of the model-based regime threshold values. So this blue bar here is for the overall bias, and the color bars are for like individual factors. So we find that overall that all different factors can contribute have some positive or negative bias, but overall the bias is within 20%, which suggests that our model-based regime threshold value is reliable, which has relatively low bias. Okay, so I just talked about how we can derive this regime threshold. And the next thing is to apply this to this satellite data. So here I'm just showing you is temporal retrieved warm season average of NO2 and formaldehyde. So as I just mentioned, that temporal is the geosynchronous satellite data, which can give us this hour information of NO2 and formaldehyde. So this was supposed to be animation, but here I'm just showing you here is just at 7 a.m. local time what is distributions of NO2 and formaldehyde over the US. And one thing I want to mention here is that Tempo is a very new satellite product, which is currently still in this provisional status. So which means that these products that has been validated with limited environments, but they still need more comprehensive evaluation. So because of this, here we're just focusing on this warm season average of this NO2 and formaldehyde from Tempo, which could hopefully reduce these random uncertainties of satellite retrievals. So this figure I'm just showing you is based on Tempo observations, the downward variations of the formaldehyde to NO2 ratios in 7 US cities. So we choose these cities because these cities are mostly in these ozone non-intimity areas where the ozone is above the standard. And the one thing that we found very interesting is that we found that all cities show very different downward patterns of this formaldehyde NO2 ratio. Like some cities show this peak of this ratio around 11, like some show the peak around 12, and some even show increasing trends throughout the day. So that is from the satellite data. But if we were to look into what is in the model, so this figure on the right is showing you based on these geochem simulations, what the model thinks that these downward variations should be. So we can see that from the models, the model shows that all the cities show these downward patterns are more or less the same, that they all peak around 2 p.m. local time. So the satellite and the model difference tells us that there's still something that we don't quite understand either in the model or from satellite. So this may be something due to these differences of emission patterns in different cities, or could be due to this boundary dynamics, or could be something that could be due to this retrieval uncertainties of satellite retrievals. So that is something that we are trying to understand, why there is intracity variations and why the model is not able to capture that. Okay, so I just talked about that we can from satellite, we can have this ratio, and combining this with this model-derived regime threshold, we could then identify what is this ozone production in different cities. So this is showing you, for example, is for these 7 US cities, what is the regime composition at different times of the day. And this is showing like the regime fractions. And the orange are NOx saturated, the yellow are transitional, and the green are NOx limited. So one thing we can see here is that we found that for these cities, the ozone formation tends to be dominated by these NOx saturated regimes in the morning, but they all make a transition in the afternoon. And in the afternoon, these cities are dominated by these NOx limited regimes, which you can see in these green colors. So this the panel on the bottom is showing you is these spatial distributions of the duration of the NOx saturated regimes, which basically representing how long that for each area they stay in these NOx saturated regimes throughout the day. And typically these red areas they represent these areas which they tend to stay in these NOx saturated regimes, which you can see only mainly occurs over these urban cores. But the blue areas are the areas which they tend to stay in the NOx limited regimes, which you can see mostly occurs over suburban areas. So the one point that I want to make from here is that as you can see that the ozone production regimes can vary a lot from morning to afternoon, from urban to suburban. So this is really demonstrates how this like the high frequency and full coverage temporal observations can now allow us to see these variations of ozone chemistry. Okay, so that is what I'm talking about how the impact of these of anthropogenic emissions of these ozone chemistries in cities. And over the US, and you may know that another challenge we currently have is wildfires. And this figure is showing you in California and Canada, the annual burn area. And we can see that in California, for example, the 2020 is it's really abnormal years, and in Canada, the 2023 is an abnormal year. And the extent of burned area in these 2 years has never been seen and even comparable with any years in the past several decades. And even when we look at this overall trend of this annual burned area, we can see that this annual burned area has more than tripled in California and more than quadrupled in Canada. So with this increase in wildfires in North America, it actually brought a lot of these air quality crises. And the increase in wildfires actually, in California, for example, the increase of wildfires offset these air quality improvements that we have achieved from decades of emission controls. So this figure, for example, is showing you is the annual average of PM5 in California. And you can see that the annual average of PM5 in 2020 is more than double than the level of PM5 in 2006. And if we were to remove the influence of fires, which is shown you as this blue line here, we can see that the PM2.5 should follow a decreasing trend, which is largely due to this emission control. But because of the increase in wildfires, we actually see there is an increasing trend of PM2.5. And the level of PM5 in recent years is actually much higher than this EPA new standard. And let's just talk about this impact of wildfires on PM5. So which is largely due to these wildfire emissions of aerosols like black carbons and organic carbons. But besides the aerosols, the wildfires can also emit a huge amount of reactive trace gases. So the wildfires, they can emit a lot of carbon monoxide, which is a pollutant. The wildfires can also emit a huge amount of greenhouse gases. And the wildfires can emit reactive nitrogen, like nitrogen dioxide is regulated as air pollutant. And the wildfires can also emit hundreds of perhaps thousands of different volatile organic compounds. And some of these organic compounds can be more harmful to human health, and they are regulated by US EPA as hazardous air pollutant. So one example of this hazardous air pollutant is formaldehyde. Which we are just already introduced but in this case, formaldehyde itself is also an air pollutant. And these photochemical reactions between NOx and VOCs can also lead to the formation of ozone, which again is an air pollutant. So that is to say that the wildfires can have a large influence not only on PM, but also on this air quality of these gas air pollutants. So what I'm going to focus on for the next part of the presentation is to think about how we can use remote sensing observations to better understand the influence of fires on NO2, ozone, and formaldehyde. Okay, so to use remote sensing to look at the fire plumes is actually very challenging. So one of the main challenges of using satellite data to look into these ozone fire plumes is because of this interference from smoke aerosols. So this figure I'm just showing you is a snapshot of the satellite retrieved NO2 and formaldehyde for several fire plumes that occurred in September in 2020 over California. So we can see here is that, say, for example, for formaldehyde, that there are a lot of these white areas, which means that they are data gaps. And essentially that from these operational retrievals, we cannot see anything about these fire plumes. So this is largely because of this a huge amount of aerosols coming from these fire smokes that kind of obscure these signals that the retrieval algorithm thinks that these are so very uncertain that it gave you like to just basically throw out these observations. So what we are doing in our group is that we are trying to improve the retrievals of unturned formaldehyde for fire plumes, and we are just developing these retrievals, which we call these trouble fire retrievals. And for these new retrievals, we make two updates. The first update is that we are replacing these prior profile informations in these operational retrievals with fine resolution geochem simulations. And another more important update is that we explicitly account for the smoke aerosol effects on these retrievals by using radiative transfer models to calculate the scattering rate so that we can account for this aerosol influence on the retrievals directly. And this figure on the right is showing you the comparison of our updated retrievals of NO2 and formaldehyde. And we can see that with our updated retrievals, we're now able to recover some of the observations that are labeled as missing values. And we also see that there is a larger enhancement of NO2 and formaldehyde in fire plumes in our updated retrievals. So using these updated retrievals, what we do is that we're trying to look at the influence of fires. So to look into the fire influence, what we do is that we are using a NOAA's hazardous mapping system of HMS smoke products to identify the areas that is affected by smoke versus without smoke. So this figure, for example, is showing you based on its smoke products, the number of the days affected by fire smoke in California. And you can see that in 2020, because of the intensive fire season and the California, most areas can have more than like 60 or 70 days of these smoky days. So what we do is that we are using these smoke products to find out these days without smoke and versus the days with smoke. And we look at the change of this NO2 formaldehyde under the fire smoke at the same meteorology, which we can then infer as these fire-induced NO2 formaldehyde. And then we do is that we use a modest fire-related power product to associate each individual fire smoke with fire locations. And then we run these dispersion models to calculate plume age, so which can allow us to see if this plume is fresh plumes or aged plumes. Okay, so this is the method, and this is showing you the results. So this figure is showing you the change of nitrogen dioxide under fire smoke in California in 2020. And this is showing you for formaldehyde. So what we can see here is that and then while we generally think that the fire influence on air quality are episodic, but because of this long and intensive fire season in California, we do see that there is a big increase of nitrogen dioxide level at the annual level. And you can see that the annual NO2 has actually increased by over like 50% in those fire intensive regions. But then if we look into this from formaldehyde, similarly for formaldehyde, we do see that the fires can increase a lot of formaldehyde. And the increase of formaldehyde on the fire smoke is actually more extensive. That can extend all the way from these source regions all the way to these downwind urban areas. So this is from the maps of this change of NO2 and formaldehyde. So if we were to think about to look into this in another way, to look into the evolution of NO2 and formaldehyde in fire plumes. So this is, for example, showing you this evolution of NO2 and formaldehyde as a function of plume age. So what you can see here is that in this in the fresh plumes, there is a larger increase of nitrogen dioxide. So this, but this increase of NO2 declines very quickly. So which is largely because of the short lifetime of NO2. But for formaldehyde, we see there is a smaller increase of formaldehyde in these fresh plumes, but the increase of formaldehyde declines more slowly. So that in these aged plumes, for these very old plumes that age longer than 8 to 10 hours, we can still observe about 25% of increase of this formaldehyde. So this figure showing you is this change of the formaldehyde to under ratio as a function of this plume age. So what we find out is that in these fresh plumes, there is generally a decrease of the ratio, which means that the ozone production has become more NOx saturated. But in the aged plumes, there tends to be an increase of this ratio, which means that the ozone production has become more NOx limited. So what does this mean? So we can now just let's come back to this ozone isopath again. And so what we find out is that And the fire-induced net increase of the nitrogen dioxide is more concentrated in these source regions, which are typically in these forest regions that is typically NOx limited. But the increase of the formaldehyde is more extensive, that it can extend all the way to these VOC limited urban areas. So as a result, what we see is that there is a larger increase of these NOx in these NOx limited forest regions, and there is a larger increase of VOCs in these VOC limited urban areas. So in both situations, the fires can lead to can favor this in ozone production, but for different ways. In NOx limited regions, it's more NOx, and in the VOC limited regions, it is more VOCs. So essentially, the fires are just providing the ingredients that they are most needed. And for forest, they need more NOx, so there's a larger increase of NOx. And for urban, they need more VOCs, so there is larger increase of VOCs. And essentially, for both situations, we will see an enhancement of ozone production. So I just talked about how the fires can influence ozone production in terms of the precursors. As you know, that the fires also can emit a huge amount of aerosols, and the aerosols can also have a large influence on the ozone photochemistry. And so the aerosols can, on the one hand, the aerosols can scatter, absorb sunlight, which can reduce the photolysis rate. And we call this as the radiative effects of aerosols. And on the other hand, the aerosols, they can also react with these hydroxyl radicals through these heterogeneous chemistries, and which we call this as a sinks of Hawks. And this is what we call these chemical effects of aerosols. So Jessie Shen, who is a postdoc in my group, so she has been using model simulations to try to figure out what are the influence of the smoke aerosols on ozone photochemistry. So essentially what she did is that we are using these chemical transfer model simulations to track this loss of these Hawks in these ozone-NOx VOC systems. And if the Hawks is mainly lost through this reaction with NOx, it is considered as NOx saturated. And if it's mainly lost through these self-reactions, it is NOx limited. And if, on the other hand, if this is mainly lost through this heterogeneous chemistry by taken by the aerosols, it is considered to be the heterogeneous chemistry inhibitor genes. And if there is larger loss of Hawks due to these radiative effects of aerosols, then we would consider this to be light-limited regimes. So essentially, for fire plumes, that we are introducing two new regimes. One is the heterogeneous chemistry regimes, and the other is the light-limited regimes. And we now have 4 regimes. Okay, so this is what the results. So this figure is showing you in California and the ozone production regimes during the fire season. And you can see that especially in September, a lot of these fire source regions are in these light limited regimes, where there are a huge amount of aerosols. It just creates a dark environment that inhibited this ozone production. But downwind from these source regions, we see there is a large increase of aerosols that leads to a heterogeneous chemistry inhibitor genes. And from this, we can see that the aerosols does have a big influence on the ozone productions. And we should also account for this aerosol influence. Okay, so this is for these fire plumes. But then if we think about globally, the aerosols do not just exist in fire plumes. And globally, in many regions of the world, we have high PM2.5 pollutions. So this is figure is showing you based on satellite data, the spatial distribution of satellite PM2.5, of a surface PM2.5. And we can see that many regions like in India, Africa, there is also high level of PM pollution. So this brings a question about how this would influence on the ozone production regimes globally. And there has been some modeling studies that suggest that because of the high PM in these regions, that they may actually inhibit this ozone production in these regions. So this then motivates us to think about whether our true regime method based on NO2 and formaldehyde is also applicable globally. And so to account for the aerosol influence, so what we do is that we are introducing one more variable beyond this formaldehyde NO2, which is the PM2.5. So this is based on, so we are currently using a satellite-based PM2.5 product that is developed by Randall Martin's group at Washington University in St. Louis. And as we're introducing one more variables, we are having 3 regimes, NOx limited regimes, NOx saturated regimes, and aerosol limited regimes. And so this is showing you how we do that. And essentially, as we are introducing like one more variables, and this ozone isoplex that I just showed you are two-dimensional, and now we are changing it from two-dimensional to three-dimensional. So this is showing you basically this three-dimensional isoplex that is mainly calculated based on models that by tracking this dominant loss of Hawks. So it is red areas that are representing those NOx saturated regimes where it is mainly NOx and Hawks are mainly lost through the reaction with NOx, and the blue are aerosol regimes, and the green are mostly these NOx limit regimes. And from this ozone isoplex, from this three-dimensional ozone isoplex, we could then identify these three regimes. And so you can see here is that at the low level of PM, the ozone production is either NOx limited or NOx saturated. But as we further increase these PM5 over this area, as we can see that we start to see the aerosol blue regimes. At a very high level of PM, it can be either NOx saturated or aerosol inhibited. So if we take a slice of these three-dimensional isoplex and to look at into two-dimensional at a given PM5 level, we can see that these aerosol inhibited regimes generally tends to occur in between these two regimes. Okay, so that is like the method that we're using to go from two-dimensional to three-dimensional. And this is showing you the results of the global ozone production regimes. So as we're introducing like the aerosol regimes, we do find that globally there are many regions showing this ozone production is aerosol inhibited. So based on this global satellite data, this is showing you based on this global satellite data with the other regimes in globally. And we can see that, for example, in China, the most polluted regions are still in these NOx saturated regimes. But in between these NOx saturated and NOx limited regimes, we do see some of these aerosol regimes. And we also see similar aerosol regimes in like India, Africa, and also over some Amazon forest. And also we see there is a huge amount of aerosol regimes in Canada in 2023, which you can imagine is due to this wildfire smoke. But in US and Europe, where we have relatively low level of PM, we see that these regions are mainly in these NOx limited or NOx saturated regimes. Okay, so by combining satellite observations for 2 decades, we're then able to look into how these ozone production regimes have changed globally. So this figure is showing you this global change of these regime fractions for NOx saturated and aerosol inhibited regimes. So I want to mention here is that globally the ozone production is still NOx limited, dominated by NOx limited regimes. But we do see that they're about like 4% to be NOx saturated and about 5% to be aerosol inhibited. And we see that the fraction of the NOx saturated regimes doesn't change much over time, but there is actually growing fractions of the aerosol inhibited regimes, which suggests that aerosol is playing more and more important roles into the ozone production. But actually, one thing that I want to mention here is that there is actually a very large uncertainty with this aerosol interactions with ozone. And this is a lot of research is currently trying to work on. But by using remote sensing data, we are able to find out where likely in the world that this ozone production is aerosol inhibited. So this may also have some implications for mitigation strategies. For example, in regions like in India, there has been a lot of efforts to reduce the PM pollution, but the reduction of PM could actually make the ozone pollution even worse. So that brings a question about how we can effectively control these air pollutions for different air pollutants together. Okay, so that is the last slide, and this is some take-home messages. So we show that how we can use satellite data for both urban and fire plumes by using TEMPO, which is a geosynchronous satellite data, and TROPOMI, which is a global satellite observations. And so this is like so our research has been mostly funded by NOAA and NASA, and these are some references if you're interested. Please check out. Thank you very much.
Right. Thank you so much. Thank you so much, Xiaomeng. Any questions? Yes.
I found it interesting that trend from city center had changed from those time periods. That was only Chicago you were showing, right? Did that trend hold true in other cities? And if so, did you look into what maybe infrastructure or policy changes locally may have led to those changes?
This is a really good question. And in our paper, we do some analysis for both Chicago, New York, and Los Angeles. And we see similar trends for all these different cities that with these reductions of NOx emissions, that there is a change of this urban rural gradient of NO2 and of NO2 for all these cities. But for Chicago, we see this trend is most clear, which I think is because of these cities are like inlines, that is like there is a hotspot of this hotspot of NOx emissions in the cities that you can see clearly there is urban rural gradient. And for New York, we also see this kind of the urban rural gradients. But in New York, that it's kind of dependent on this wind direction. So that is one thing that we didn't account for in our analysis, is how we define this like upwind versus downwind directions. And in New York, it's kind of like some like Long Island is more like this like upwind direction, right? And like in New Jersey, it's like in downwind direction. So that is something we didn't look into. But overall, we do see this trend still holds. But if you look into that, maybe depending on whether you look into that, this may be a little bit different. And also, as you just mentioned, that the change of these infrastructures, changes of these emission sectors, they also influence these down patterns, or they influence spatial patterns. But this is also maybe potentially could be one limitation of satellite data, is that the resolution is only about 12 kilometers per ohm that we look into, that it could be limited to resolve a lot of these locally, how this emission source would influence these urban rural gradients. That could be something that with in-situ environments that we can have better pictures.
Thank you.
I'll ask a question. So if you go back to your slide showing the global ozone production regime,
Yes.
like I noticed this map, I mean, it's kind of looks like, I mean, if you look at the aerosol area, it kind of looks like the PM concentration, but not like exactly the same, right? Like for instance, some of the high PM regions that are like the dusty Sahara or Middle East or Northwest China, they don't show up. So is this because of the model is actually able to tell which type of aerosol has the higher effects, or like what drives this differences between PM concentration and this regime?
Yeah, this is a very good question. And indeed, that different types of aerosols can have very different influence on this. So what essentially is influencing these in reactions with HO2 uptake coefficient is this aerosol surface area. And for PM5, it's just mass concentration. And depending on what is the size of the aerosols, this aerosol surface area is very different. And generally speaking, like say for these dusty regions, they are dominated by coarse particles. So the coarse particles are heavy, but they have like smaller surface area. So that is why that for these areas, even though they have large amount of this aerosol mass, but the aerosol surface area is relatively smaller. It is only the regions that we are dominated by these fine particles, like say like in China and India, these regions are dominated by this sulfate, nitrate, these small particles. They tend to have a larger surface area. So in our calculations of these regions, we do also account for these spatiations of different aerosols. Even though we cannot differentiate different types of PM from satellite, but we are using like model simulations to give us a sense about these compositions of PM. So the composition information is from model, and it's true that it can be very different for different species.
Yeah, you can pick.
All right, yeah, thank you for this nice talk. A question and maybe 2 comments. Just to go back, your formaldehyde to NO2 ratio derived from the satellite hinges on your geoschem model in a way.
Yes.
And so I was wondering, you assume the geoschem model then to be the absolute truth? Or this has an error too, and it was not really clear to me how the error of the model goes then into the error of the retrieved formaldehyde NO2 ratio. That was the question. And then the comment is, as an aerosol person, measuring uptake coefficients. Yes, so the Hopf mechanism in the forest fire plume, of course, as you say, it depends on surface area. There will be humidity, viscosity.
Yes.
And the uptake, if there's so much, it may saturate and slow down because there's too much on the surface. So that it's really complicated. And we are still working to get the details on such large scale models into it. And the problem is, I'm struggling a lot that is on mass based and not particle size distribution. It's a huge issue. So anyway, that's a comment. But then my second comment to that, you showed Hawks, that is with sunlight. So I would now challenge you, half the day's night, there's no Hawks, there's no OH, but you have NO2 N2O5, NO3 chemistry. And so your plume is several days en route. So yes, for 12 hours or 8 hours, that chemistry may be right and affect your NO2 and your formaldehyde NO2 ratio. But at night, you have NO2, NO3, N2O5 uptake. And you start the morning with a complete different NO2 budget. So your formaldehyde and NO2 ratio will be completely different in the morning. Well, sorry, now I have a third comment that I forgot. It's only comment, you don't need to answer to that. But we had a 6 weeks aircraft fleet campaign here, Gotham. And it's amazing. I'm not surprised that your retrieved formaldehyde NO2 ratio is different than what Geochem predicts or suggests the profiles over the cities. We saw biomass burning plumes diluted, lingering on for weeks over Long Island, New York City, and that's not captured by Geochem data. We had filaments of these plumes all around, and of course, your satellite will be sensitive to that. So I mean, really for weeks, we saw, oh, maybe today we are affected by smoke from Canada, but we had these things for 4 weeks or so all the time. It really bothered us because it changed the chemistry and everything. And so Geochem will not catch that. And so as you compared retrieved ratios versus Geochem, I'm not surprised they're different. I would almost bet more on the satellite than but that comes back to the first question, or you are really tied to this model to make sense out of the satellite data. It's always a crux of it.
Yes, this is, so you have a lot of comments that I need to digest a little bit.
No, the comments you don't need to answer.
Yes, but
just the uncertainty model and.
Yes, but to answer your first question about these uncertainties of model, and it is indeed potentially a limitation of our method is that a lot of this is derived from model simulations. And our group is currently working on evaluating this model-derived this relationship using in-situ environments. So we have Pandora, we also have TAMS environments, but they're still kind of like limited in spatial coverage. And we do see that models does have some problems, especially problems more with this VOC to formaldehyde part. That could potentially also influence this uncertainty, but that's something we are working on. So what else? And I think it's, and also the other thing that I want to mention here is that we're actually using like 2 approaches. So one is what we call like bottom-up approach that is based on from model simulations that we are building these from these steady state models into these with these 3D models. So that is more subject to uncertainties of models. But on the other hand, we are also trying to just make this top-down approach that we directly link the satellite retrievals with ozone observations. So this does not give you like process level understanding of these things, but it can give you indicating about whether this satellite data is correlated, like statistically correlated. If they do, they still show that they are good. But to understand this to understand more comprehensively, that I think that we can have these 2 approaches like this complementary. But it's still that there's some more work to be done. And I really appreciate all your suggestions. And I think I wish that I have a pen that I can write down these comments, but we can communicate later. Yes.
No, thank you. Very fine work.
Okay, that's great. Thank you. Yes, right.
Great work, Xiaomeng. And I have a question regarding the wildfire caused spreading of formaldehyde. As we know, that formaldehyde also is a very short life chemical cells, just like NO2. But I'm kind of curious why formaldehyde is more spread out than NO2, as you show in California.
Yeah, that is a great question. And I actually have one more slide that I didn't get a chance to show. That is in our paper, we are trying to figure out why there is formaldehyde even in very old plumes. And we are using like Geochem to separate this formaldehyde from primary sources for secondary sources. So what we find out, that short answer is that a lot of formaldehyde in the aged plumes is due to the secondary product from oxidations of these low reacting VOCs in the aged plumes. So the formaldehyde you see in the aged plumes, they are not from its source, but they are actually being produced along these viral plumes, so they can see a consistent increase of formaldehyde.
We'll take one last question from Steve.
Yeah, thanks. Yeah, it's very impressive piece of work, your body of work. there was an earlier question, is a high aerosol region, why is there no ozone suppression in the Sahara? I think it's because there's no ozone production in the Sahara, so therefore, no matter how much aerosol you have, it's not gonna suppress any ozone formation. But I was very intrigued by your three-dimensional plot where the amount of aerosol, yeah, that one, where the amount of aerosol is a third dimension in the Ekman diagram. But you must then distinguish in those calculations sort of what Daniel was getting at, whether it's the free radical suppression versus the radiation suppression. And I think you need probably another dimension in this to include those two components of the aerosol of the aerosol suppression. Can you comment on that?
Yeah, this is also a very good question. And I have to say that for this kind of work here that we are trying to use satellite data, we kind of are not unable to differentiate radiative effect versus this heterogeneous chemistry effect. And here we are only defining it in terms of these aerosol heterogenes to be that these are the Hawks meaning loss through these chemical effects. So the radiative effects are not accounted here. That is something we are trying to figure out a little bit more.
It's really chemical more than radiation.
Yes, but in reality, yes, it should be that these radiations can also have an influence, but it's just currently this three-dimensional isoplot cannot account for that. That's something that I'm still trying to work on a little bit more, trying to figure out if there is a way to do that. So we could do that in models. In that you can use models to simulate these like radiative effects of aerosols, but it's kind of tricky to do that just based on satellite data. So still not doing that.
Make a visualization of that.
Yes.
Thank you.
Oh, that's a great idea.
Yes, but I think it's something I can try to change a little bit, maybe next version.
All right, well, thank you, Xiaomeng. Thank everyone for taking the presentation.